So in the last lecture, we talked about the idea that we have conjugated and isolated dienes, and the isolated or non-conjugated dienes undergo reactions that are the same as just a normal alkene, except that there's two double bonds that can react, so twice as much stuff can add, 2 equivalents HBr, 2 Br2s, etc. Before we go to the reaction of dienes, we need to take a step back and we need to look at a specific special position relative to a double bond. And that's the carbon that is attached to the double bond. This position is called the allylic position. And the allylic position turns out to be the carbon attached to the double bond. And when we form a radical or a carbocation at this carbon, it turns out that those intermediates are stabilized by resonance. So we have to talk about the allylic position, and more importantly, the allylic intermediates. We'll start with radicals and then move to carbocations before we can talk about the reactions of conjugated dienes. So let's start with the formation of allylic free radicals. So if you were to react Br2 in light in a free radical halogenation, what you would do is we would usually look for a tertiary position, since bromination is the most selective there, or secondary or primary. But what we find is that when we brominate this propene, we end up substituting one of these hydrogens for a bromine, and so we end up brominating that allylic carbon. And the reason for this is pretty straightforward. The allylic radical turns out to be stabilized by a number of different resonance structures that you can draw. So for instance, if I take this allylic radical and I split this double bond up and give each carbon one unpaired electron, and then pair up the unpaired electron with the center carbon with the one on the left, I can form a double bond. And so there's two equally stable resonance structures for this allylic carbocation. And so we find that the selectivity of the allylic position is at least as good as a tertiary position, probably about 1700-ish to 1, depending on whether this is a primary, secondary, or tertiary carbon. Now, that means that if I was to take something like this molecule and do bromination, light, room temperature, that I would get the bromination to occur then at the allylic position, whether this was secondary or tertiary or primary. That's going to be our most selective position, is next to the double bond. Okay. Well, there's one small problem with the reaction the way that I wrote it here. And that is, I've written the free radical halogenation as bromine light at room temperature. What would the product of this reaction be had I have left off the light and room temperature? In other words, I would have written the reaction like this. What would you have written the product to be, particularly back in chapter 8? If you said, well, I would have added the bromines trans to form 1,2-dibromo butane in this case, you'd be right. What does the light and the room temperature do? Absolutely nothing. So when I write the reaction here as a free radical halogenation, that's not actually what's going to occur. I'm not actually going to free radically halogenate. Instead, I'm going to add bromine across the double bond, which means if I go back here to this reaction, I'm actually not going to get this product. Instead, I'm going to get bromination again across carbon 1 and carbon 2. But if I was to do free radical halogenation, I certainly would free radically halogenate at the allylic position. So What we need is we need a reagent that won't add bromine but do free radical halogenation. And this is where we introduce the idea of using this reagent. This reagent is called NBS. It's N-bromosuccinimide. And it's a brominating reagent that allows for free radical bromination without addition of Br2 to the double bond. So if I wanted to free radically brominate this molecule, instead of using Br2, whether there's light and room temperature or not, I'm going to do addition. Instead, what I would do is I would say, okay, I'm going to go ahead and add NBS to this, and the NBS then would free radically halogenate at that position. So from now on, when we want to do free radical halogenation of a double bond at the allylic position here, we need to use NBS and not Br2 because Br2 would add to the double bond. And there, I think there's also an NCS for N-chlorosuccinimide if I wanted to chlorinate. But we have to change reagents because I want to do free radical halogenation and not add bromine across the double bond. Now you still, if I gave you an alkane and I said, okay, take that alkane and add a bromine to it or substitute a bromine, you could there use either NBS or bromine light at room temperature because there's no double bond that the bromine can react with, so it'll always undergo free radical halogenation. But when I want to brominate an allylic position, I need to change my reagent now to NBS instead of using bromine at room temperature and light, or even bromine greater than 300 degrees Celsius. Okay, so we just need to remember that when we're going to do free radical halogenation. We're going to brominate at the allylic position, and we need to use NBS as our reagent. Again, I might give you the structure of NBS and have you recognize that it is NBS and we'll do free radical halogenation. I wouldn't ask you to write the structure. You could just write NBS as a reagent, but you need to recognize NBS as the brominating reagent. Now, let's move to allylic carbocations. And if you form an allylic carbocation, you have the same possible resonance structures. So let's say I form this allylic carbocation. I could move this pair of electrons here to form a second resonance structure. Now, at first glance, you might say, but wait, you just wrote a primary carbocation structure. Well, this isn't primary, it's primary allylic. Because I can form two resonance structures, that makes this carbocation actually more stable. Of course, if we have resonance structures for allylic carbocations, that means we have our resonance hybrid. And in this case, what would happen is that we would average out the bonds. So we got single bond, double bond. The average is a partial double bond. We've got a double bond here and a single bond here, which means the average is a partial double bond. And then finally, the plus charge on this carbon, neutral here, so that's delta plus, neutral plus 1, average delta plus. So because this is symmetric, you can think of each one of these carbons as having 0.5 of a plus charge. Again, it won't always be that way, and in general, I'm only concerned about the delta plus charge as opposed to the knowing the exact charge. In this case, because of the stability of both of these, they're pretty much the same. So that's why we have an even split. Okay. So what is the structure of an allylic carbocation? Well, for that allylic carbocation that we just looked at, that's the CH2 double bonded to the CH with the CH2, in this case with the plus charge over here. What I have is all three carbons are sp2 hybridized. And so that means there's empty or there's p orbitals in the sp2 hybridized carbons. In this case, two of those p orbitals might be overlapping to form the double bond, and the other orbital would be empty, but realize that in the resonance hybrid, what's going to happen is that we're going to end up with sharing of those two p electrons over the entire course of the three atoms. So we'd have partial double bonds, and then our delta plus charge being spread out over the two N carbons. So this would be what the resonance hybrid looks like. And of course, what really happens is that these electron clouds then become kind of smeared together, so that what we see is a longer pi system here over those three carbons. So kind of looking like the picture that we drew for a conjugated diene, only in this case I have two electrons split over three p orbitals or three atoms. So if we were to look then at the charges on this allylic carbocation that we got from propene earlier, what we would see is they each have delta plus charges on both CH2s. And again, since the two resonance structures that were used to draw these have the same energy, each of the carbons would have exactly the same charge, which would be 0.5. You can see that in this diagram. Here's one of the diagrams that your book uses to show partial charge. For those of you that were in the lab last semester, we did a demonstration of how we get these from the computer. These blue areas are areas of delta plus charge, and the red areas are usually areas of delta minus charge. But the key is, notice the shading on both of these carbons. That indicates that they have the same overall charge. They have to, because this is a symmetrical allylic carbocation. Will that always be the case? No, we'll look at an asymmetrical one here in a moment. So here's a potential reaction that involves carbocations that are allylic. Let's say that I took this molecule, and I'm going to put a chlorine here, and I was to react this with water. Now, you would normally look at this and say, well, that's a primary carbocation. Water is a weak nucleophile, therefore the mechanism has to be SN1, but primary alkyl halides don't undergo SN1. True, but this isn't just a primary alkyl halide. This is a primary allylic one. So if I was to lose the carbon-chlorine bond, I would actually make my allylic carbocation, and then I would have two resonance structures for this allylic carbocation. The true resonance structure of this allylic carbocation looks like this. And if I'm doing this reaction, the question is, the water is now going to come in and it's going to add to one of those delta plus charged carbons, and I'm going to end up in this case getting two potential possible products, although they would be identically the same. Now, one of the problems that we have with this resonance hybrid, and this resonance hybrid is the true structure, but it becomes difficult to write the structure or write the mechanism using the resonance hybrids, simply because what we end up with is we end up not knowing, well, where do I add my water? So if my water is going to come in and add, what's it going to add to? Where's the double bond going to end up? So instead of doing the reaction from the true structure, the resonance hybrid, what we do is we treat each individual resonance structure as if it was the structure, and then we do reactions with those. For instance, if I was to take water and react it with this primary allylic carbocation, I would form the oxonium ion, and then I would lose my H+, to form the final product. If I was to react water with this carbocation, I would end up with this oxonium ion, and then I would lose the H plus, to form the final product there. Now, these are the same product. So in this case, it's not these two resonance structures because they're of equal stability. It turns out they give the same product. So what we will do whenever we encounter the carbocation resonance structures is I'm going to treat each one as if it was the intermediate of the reaction, and then add the nucleophile to those to get my different possible products. And this is just a lot easier than reacting the water with, let's say, the resonance hybrid, where I can become confused as to what to do with the double bond. Where should the water add? It should add to the delta plus charged carbons, but it's just easier to do it this way and treat each resonance structure as if it was a real structure, which we know from last semester it isn't. So here's just the example of that, showing the difficulty in adding the nucleophile. If we added it to carbon A, I would end up with this product. If I added it to carbon B, I would end up with this product. And so, again, it's a lot easier to just say, okay, let's react the nucleophile with this resonance structure to get this product. Let's react the nucleophile over here with this carbocation to give us that product. Now, what happens when the carbocations become, when the allylic carbocations become asymmetrical? So for instance, let's say that I add HBr to this alkene. Okay, the first thing I'm going to do is I've got an H plus and a Br minus. I'm going to go ahead and add the H plus to the double bond. I'm going to do this by Markovnikov's rule. So Markovnikov's rule would say I'm going to add the hydrogen to the carbon with the most hydrogens, and the bromine to the carbon that's most substituted. So I'd end up with the H there, and then that would leave a carbocation here. And the Br minus would just come in. And I added HBr Markovnikov, okay? Not that big a deal when there's just a single double bond. The allylic carbon doesn't play a role. But now what I'm going to do is, now I'm going to take that alkene and I'm going to make it a diene. And now I'm going to add HBr to it. So again, I've got H plus, Br minus. I'm going to take this double bond, add the H plus to the carbon with the most hydrogens. So I'm going to do Markovnikov's addition, and then I'm going to end up with a carbon with 3 hydrogens attached to it. I'm going to end up with this CH that has a positive 1 charge, and then my double bonds there. Now looking at this carbocation then, what I see is it's allylic. So I could say, okay, well, I'm just going to take this pair of electrons, move here. So now what I'm going to end up with is, I'm going to end up with the double bond there and the positive charge on that carbon. Now, I've got 2 resonance structures. I could write the resonance hybrid, but I'm not going to for the moment. The Br minus could come in and add to this carbocation, which would then give me this product where I've added the H and the Br, then Markovnikov. But now notice I get a new product. If I added the Br minus to this resonance structure, I'm going to end up forming this product, where now if I started by numbering these carbons 1, 2, 3, and 4, in this product to the left I added the H and the Br to carbons 1 and 2. In the second resonance structure I added the H and the Br to carbons 1 and 4, and the double bond is now between carbons 2 and 3. So in a way it kind of looks like this product over here has been rearranged. And in essence it really hasn't, because remember the true structure of this carbocation is the resonance hybrid. But certainly we would have predicted this product. We would not have predicted this product to form unless I go through step by step and write the mechanism. Well, these products have names. This is sometimes called the 1,2 addition product, simply because I've added the electrophile and the nucleophile to carbons 1 and 2 respectively. And what we're doing is we're adding to a 4-carbon diene system. So the 1 and the 2 aren't IUPAC names, they're the relative numbering of this diene. And here I would call this the 1,4 addition product, because what that is the addition of the H and the Br to carbons 1 and 4 of that conjugated diene system. Okay, so when I do reactions of conjugated dienes, because of the resonance structures that are possible for the allylic carbon, I'm going to end up with a new product over here that I wouldn't have predicted until I started talking about the resonance structures of allylic carbocations. So that's what our addition reactions to conjugated dienes looks like. So here's just another version of that. And in this case, unfortunately, in this old slide, I numbered the 1, 2, 3, 4 from right to left. But notice here I've added H plus to carbon 1. There's my carbocation. My double bond moves there to give me the second resonance structure. Then treating each one as its individual reactant, I would have the Br minus add to this resonance structure to form my 1, 2 product, and then have the Br minus come and add to the carbocation on carbon 4. That would then give me my 1, 4 addition product, where the double bond is now moved to between carbons 2 and 3. So this is just the nice version of what I just did. Going back now and looking at those two carbocation intermediates, if we start over here and I added the H on this carbon to begin with, so this is carbon 1. Here is my resonance structure for the first resonance structure where the carbocation is on carbon 2, and then here it is for carbon 4, the second resonance structure. Now, the resonance hybrid of this looks like this. This is the average structure. That's the resonance hybrid. Let me ask a question. If I gave you these two resonance structures and I asked you which one is more stable, could you answer that question? If I would give you, well, let's just stop there. So which of these two resonance structures is more stable? That's something to think about. And then, if I gave you this resonance hybrid and I asked you the question, which carbon has the greatest delta plus charge? Could you answer that question? And those are actually could be two different questions with two different answers depending upon how you basically look at the problem. Let's do the resonance hybrid one first. Which of these two carbons has the greatest delta plus charge? If you said it was this carbon, you're right. Why? Why does this carbon have more delta plus charge than this carbon? Well, the reason that it has a greater delta plus charge is because what does this carbocation look like? If this was a C plus, like it is up here, what kind of carbocation is it? Well, I'd put in quotes that's a secondary carbocation. How about this carbon? That looks to me like it'd be a primary carbocation. So which of these two carbons has the greatest delta plus? This one. Okay, kind of the way we looked at epoxides having the greater delta plus charge. Now, if I come up here and I ask you that same question, well, not that same question, but a similar one, which of these two resonance structures is more stable? Then you might ask the question, well, what am I using for my stability? Okay, this is a primary allylic carbocation. This is a secondary allylic carbocation. But notice there's a double bond here. So which of these two double bonds is more stable? Well, I've got one with a double bond here with one alkyl group attached, and I've got a double bond over here with two alkyl groups attached. So do I know what rules to apply to these two carbocation resonance structures to tell me which one is more stable? Is it a primary versus secondary allylic carbocation, or is it a more substituted double bond versus a less substituted bond? And that's a pretty interesting question to ask because that's going to help us in looking at the overall reaction. Well, it turns out that our first priority here, the first priority we're going to use to base stability on is the type of carbocation that we have, whether it's primary, secondary, or tertiary. Tertiary is the most stable, primary is the least stable. So looking at these two structures, I would say that this one is the more stable carbocation resonance structure. The double bond then would come second. So if we had a tie between carbocations, maybe two primaries or two secondaries, then I would look at the substitution pattern on the double bond. Okay. And normally when I talk about this in class, I'll ask people and I'll usually get them to give me both answers. But in this case, I'm going to set the priority of this carbocation being the important feature and the substitution pattern on the double bond only being taken into account after, or in the case of a tie between the carbocations. So the structure on the right is the more stable carbocation intermediate. So I get two possible products for this reaction. I can get the 1,2 addition product and I can get the 1,4 addition product. Well, whenever we have two products possible for a reaction, we always ask the next question. What's the major product? And the second question that usually comes after that is why. Again, in class, I might ask this question. I might say, so which one do you think is the more stable? Well, not more stable. Which one do you think is the major product, the 1,2 or the 1,4? And people would probably give me both answers, and I would say the true answer is it depends. And then usually people are sitting there going, what does it depend on? Because all of our reactions before have had a definitive major product, but this one's going to depend on the reaction conditions. And so depending on the reaction conditions, I could favor 1,2 or I could favor 1,4. Well, how can that be? Let me get to it in a moment. But there's some terminology we need to talk about and some questions we need to ask in this process. Number one, what's the most stable intermediate? What's the most stable product of the reaction? So let's go back to this reaction here, which is the one that I did by hand all the way back there. So let me ask you a question. Of the 1,2 and the 1,4, which one is the more stable product? And you'd look and say, okay, well, these are alkyl halides. Do I have rules about a primary alkyl halide versus a secondary alkyl halide? And the answer is no, I don't have any rules about that. But I do have rules about double bonds. So is a double bond attached to one alkyl group more stable than a double bond that's attached to two alkyl groups? No. So therefore, the 1,4 addition product, because of its substitution pattern, would be the more stable product. What about the more stable intermediate? Well, we've just gone through that. If this is a secondary carbocation and we treat this as a primary carbocation, we would then say that the secondary carbocation turns out to be the more stable intermediate. Okay. So we have to be able to answer those two questions. What's the more stable intermediate? What's the more stable product? So once we answer the question of what is the most stable intermediate and what's the most stable product, that helps us then in terms of explaining how the reaction conditions will change the overall major product of the reaction. So we need to know what rules do we use for stable intermediate, what rules do we use for the stable product. That's two other terms I want to define before we get to actually answering the question of what is the major product beyond it depends. And that's what's the kinetic product? Well, a kinetic product is defined as the first formed product in the reaction. That makes sense. The kinetic product is the one that's formed fastest. When do you get the kinetic product? Well, you get the kinetic product when you either do a reaction at low temperatures or you use short reaction times. That will give you the kinetic product as the major product of the reaction. Think about free radical halogenation. Our selectivities became much more So what's the thermodynamic product then? Well, the thermodynamic product turns out to be the most stable product. How do we form the thermodynamic product as the major product? Well, we use high temperatures and long reaction times, and that'll give us the most stable product. So here we have the two different products that we can form under two different sets of reaction conditions. The first, kinetic product, which is the product that's fastest forms, you'll get that at low temperatures and short reaction times. You'll get the most stable product, the thermodynamic product, at high temperatures and long reaction times. Now, for the most stable product, if we go back to our reaction here, we already said that the 1,4 addition product is our more stable product. Therefore, I would consider this to be the thermodynamic product of this reaction. Does that mean that the other one is the kinetic product? Usually, but not always. To answer which product is the kinetic product, I need to ask this question. What's the most stable intermediate? Why would I ask that? Well, remember that the more stable the intermediate, the faster the product is formed, because the more stable the intermediate is, the lower the activation energy and the faster that that product is formed. So really when I'm talking about the kinetic product, this one comes from the most stable intermediate. So there's what we need to know to answer the question, what's the major product? I need to be able to identify the kinetic product, which comes from the most stable intermediate, which one's the thermodynamic product, which is the most stable product. And so I'm going to favor the kinetic product at low temperatures, short reaction times. I'm going to favor the thermodynamic product at high temperatures and long reaction times. So coming back here, which one of these two intermediates was the most stable? This one was, and so that means that the 1,2 addition product is the kinetic product because it comes from the most stable intermediate. So in this case, if I change a couple of groups here, I can actually make the 1,2 the thermodynamic and the 1,4 the kinetic. So what you don't want to do is link 1,2 and kinetic. You just want to know, okay, where does the kinetic product come from? It comes from the more stable intermediate. What's the thermodynamic product? It's the one that is the most stable product. But in this specific case, the 1,2 product was kinetic, and the 1,4 product was the thermodynamic one. So let's go and look at some experimental data that may come from your textbook or one that we used a few years ago. Here's a reaction of HBr and butene, the exact same reaction we've been looking at. Here's minus 80 degrees. What is that? That's low temp. What product should that favor? That should favor the kinetic product. So notice what happens. When you do this reaction, you get 80% of the 1,2 product and 20% of the 1,4 product. Well, the 1,2 product came about from having a carbocation that is quote unquote secondary, and so that came from the more stable intermediate. So we get an 80-20 ratio of products when we do this at low temperature, with the 1,2 being then our kinetic product. And of course, this is how, this data helped people come up with the idea of the kinetic and thermodynamic products. So what we're doing is kind of using the data to explain the theory, which explained the data to begin with. But notice what happens when I go from minus 80 degrees to a very warm 40 degrees, relatively speaking. I now get an 85% of the 1,4 product. Well, the 1,4 product has the double bond that's di-substituted, has two alkyl groups. Therefore, this is the more stable product. Under thermodynamic conditions, which you may say is 30 degrees that hot, well, compared to minus 80 degrees, it certainly is, then you get the thermodynamic product for this reaction. So by changing the reaction temperature in this case, I can completely change the reaction, the major product of the reaction. I can go from 80-20 to 1585 just by simply changing the temperature. So when we're given a reaction, we need to look at the temperature. We need to look at whether it's a short time or a long time. And then we need to determine, well, which product is kinetic, which product is thermodynamic, and then we get that final answer as to what the major product is. But none of this deals with a very important question of why. How can I change the reaction products, the major product, by simply changing the temperature? That doesn't make much sense. Well, it does when you put together this reaction coordinate diagram. And so let's go through some of the features here, because this answers the question of why. Why does this happen? Not why am I going over this because we need to understand this, or why am I taking this class, but why is this reaction why can I change, or how can I change, and why does this change major products? Well, what we have to remember is the following, that our intermediate is actually not those two resonance structures, but it's the resonance hybrid. So I got a delta plus charge here and a delta plus charge there. Now, when my Br minus comes in and adds to this secondary like carbocation, and when the Br minus comes in and adds to this primary like carbocation, we can't really invoke the fact that the secondary carbocation is more stable than the primary if this whole thing is the resonance hybrid. But here's what we do know. We know there'll be more delta positive charge on this carbon, on the secondary carbon, than on the primary carbon. And you may say, so what? Well, here's the so what. The bromine, when it comes in and adds to a carbon with more electron density, that has a lower transition state energy than if the Br minus comes and adds to a carbon with less delta plus charge on it. So when we add to the secondary carbocation, we end up with a lower transition state energy than when we add to the primary quote unquote carbocation. That gives a higher transition state energy. And of course, what does that mean? That means that the activation energies here are different. And the activation energy to form the 1,4 product is higher than forming the 1,2. So if I ask the simple question, okay, I'm starting at this resonance structure, this resonance hybrid, which product is going to form faster? You would say the 1,2 product is going to form faster. Why? Because it's got a lower activation energy. Arrhenius' equation says it will form faster. So this explains why we form the 1,2 product faster than the 1,4. It's simply that the activation energy is smaller for adding the bromine to the secondary carbocation. Now, how do we get the 1,4 as the major product? Because there's nothing I can do here to make the 1,4 form faster. Right? Even if I raise the temperature, at best I get 50-50. Because then both of these barriers would be overcome equally fast. Of course, if I lower the temperature, then I go over the 1,2 barrier a lot faster than the 1,4 barrier. But how do I get the 1,4 as the major product? Okay, and if you're going back to free radical halogenation, raising the temperature in essence makes the molecules go over the barriers at the same rate. But now what I'd like to do is I'd like to form the 1,4 as the major product, and I don't see how I can do that. Well, here's the other piece to the diagram. The other piece to the diagram is, here's the 1,2 product that I form. Since the 1,2 product is less stable than the 1,4 product, it'll occur at a higher energy than the 1,4 product is. Okay? Now, what does that mean? Well, it doesn't mean anything right at the moment. But here's what's different about this reaction that hasn't been the case up till this point. When I have this allylic bromide, it turns out that I can break this carbon-bromine bond and I can form this carbocation intermediate, which of course has a resonance structure. But wait, if I break this carbon-bromine bond, I'm right back to the intermediate. So the key thing with this allylic bromide is that this reaction is reversible. And so is the 1,4 product. I could break this carbon-bromine bond and end up right back here at the resonance hybrid of the carbocation intermediate. Allylic carbocations can form from this. What would this be? Well, this would be the first step in kind of like an SN1 mechanism, right? Lose the leaving group to form the carbocation. So the real key in this reaction is reversibility. So imagine that I'm doing this reaction at low temperatures. Well, if I'm doing this reaction at low temperatures, what happens is that I barely have enough energy to go over this activation barrier relative to this one, although some molecules will overcome the bigger barrier. But if I'll overcome the smaller barrier quicker, I'll end up with more 1,2 product. Great, at low temperatures and short reaction times, I'm going to end up with more 1,2 than 1,4. Okay, straightforward enough. But now let's go to thermodynamic conditions. High temperatures, long reaction times. So initially, I start out with my molecule at this position and got lots of thermal energy, high temperature. I go over this barrier. Okay, I go over the 1,2 barrier a little bit faster than the 1,4, and now I end up down here. But guess what happens? If I have enough energy, I can now go back up this diagram and end up in my carbocation intermediate. Well, now look at what I have. I have a second activation energy. As long as I have enough thermal energy to overcome that barrier, I basically can go to my 1,2 product, but then my 1,2 product ends up going back to the intermediate. So it's kind of like there's an equilibrium there. Then if I have enough energy, once I get over the 1,4 activation barrier, I end up down here. But this more stable product has a bigger reverse activation energy than this one had. So these two activation energies of the reverse reaction are significantly different. Now all of a sudden when I'm down here at the more stable product, I may not have enough energy to reverse myself and go back over this barrier. I might get stuck here. This is sometimes what I call the thermodynamic sink, because everything gets stuck in it. So if I have lots of temperature, lots of thermal energy, long reaction time, initially I'll form a lot of 1,2 product. But then as I reverse and I end up over into the 1,4 sink, I'll end up just accumulating product here, and particularly if I tune the reaction conditions so that I can get over all these other barriers but this one, then I'll end up with a majority of the 1,2 product. So the key is the reversibility. The idea that, yeah, low temperature, short reaction times, these two activation energies are different, and so clearly I'll form more 1,2 product than 1,4. But when I have long reaction times and high temperatures, that's when I'm going to end up with more product over here, because it's that reverse barrier that's going to keep products in the 1,4 well or sink as opposed to moving back to the 1,2. So the key thing is that's this reversibility of the allylic bromide once it's formed. The fact that that step of losing the bromide is reversible so that I can end up back at that intermediate. Okay, I know this is a little tricky, but that's how we explain why under high temperatures, long reaction conditions, we get the thermodynamic product, and under short reaction times and low temperatures, we get the kinetic product. And so that's what we have here. The kinetic product, and over here, the thermodynamic product. Okay? Now, as far as determining what is the kinetic product, what is the thermodynamic product, let me give you a couple of problems to try. I'm going to do things a little bit differently for this set of problems. Why did I just do that? Let's say I reacted this molecule with HBr. Could you write the 1,2 and the 1,4 addition products? And could you write the mechanism for forming those? And you'll need to write the mechanism because that's the only way to determine what the more stable intermediate is. Then let me make this change. I made no change there. Let me make this change and put the two methyl groups there, and now add HBr to them. And I get 1,2 and 1,4. Can you write the structures of the 1,2 and 1,4 products? And can you write the mechanism for that? Now here's what you need to know to do this. And I'd like you to try this for the next class period when we'll be discussing these results. Okay, for those of you sitting there going, well, that's Wednesday, what I'd like to do is try and reuse these lecture videos. So the next time first time you hear it, it might be Wednesday. The next time after that, it might be another day. That's why I'm trying not to say a specific day. But if you're listening to this for the first time, then it's going to be Wednesday. Here's what you need to do. Whenever we have a conjugated diene system, we always call this 1, 2, 3, and 4. And we always call this 1, 2, 3, and 4. Okay, and I could number this down here starting 1, 2, 3, and 4. I'm always going to give you symmetrical dienes, so it doesn't matter where you start numbering. But the key thing is you got to start numbering to give the 1, 2, 3, and 4, the 4 carbons in the double, single, double molecule. Okay, so that's what we need to look at. So in this case, what I'd like you to do is write the product of 1, 2, 1, 4, and then you're always going to add the H plus to start this mechanism. You're always going to add the H plus to carbon 1. And down here, you're going to add the H plus to carbon 1. Now for this problem, you might say, well, that's not Markovnikov addition. Markovnikov addition would be to add the H to carbon 2 and form the tertiary carbocation. Well, no. I'm going to define Markovnikov's rule as you add the H plus to the carbon that gives you the most stable intermediate. So if you're curious, add the H plus to carbon 2 after you've added it to carbon 1. Go back at it to carbon 2 and see. Did I really get a more stable intermediate by adding it to carbon 2? Or did I form the more stable intermediate by adding it to carbon 1? And the answer is you get the more stable intermediate adding to carbon 1. But I might ask that question on Wednesday. Okay. So what I'd like you to do is to try and add H plus to carbon 1. You'll get a carbocation at carbon 2. Draw the resonance structures. Add the Br minus, form the 1, 2, and 1, 4 product. And then can you tell me? So what's the thermodynamic product? What's the kinetic product? And be prepared for me to put these problems up on the screen on Wednesday and poll you with the clickers to see which one you thought was thermodynamic, which one you thought was major, or I didn't get it, at which point we'll go through and go over these two reactions. Okay, but I'd like you to try these two, writing the 1, 2, 1, 4 products and the mechanisms, and seeing if you can get to the point of saying which one is thermodynamic and which one is kinetic. Okay, so that's what we will do on Wednesday, I guess, Wednesday's class.